The nature of the tooth contact between spur gears is revealed here by means of straight polarized light. Note that the line of contact occurs across the face width of the teeth. As the gears are rotated, this line of contact moves along the profiles and demonstrates that smooth, angular motion results because a succeeding pair of teeth takes up the load before the preceding pair passes out of engagement. It is interesting to observe the variations in width of the contact lines as the gears rotate. Here, the load on the teeth has been greatly increased. It will be seen that the contact lines are no longer of even width from one end of the teeth to the other. They now vary due to the heavy loading and the plasticity of the material. It will also be noted that the nature, location, and intensity of the stresses change with the contact positions of the teeth as the gears rotate. When the point of one tooth contacts the flank of its mate, the stresses are shown to be of greater intensity. This pair of plastic helical gears will operate on parallel axes and be photographed with polarized light. The line of tooth contact is at an angle relative to the axes and travels progressively across the teeth as the gears are rotated. With helical gearing, if the advance of the helix in the face width is equal to the circular pitch, the gears have continuous helical action. Helical action means there is progressive pitch line contact occurring continuously across the tooth faces. For this reason, properly designed and accurately generated helical gears operate more smoothly and quietly than spur gears. We will illustrate some applications of the generating principle to the cutting of gears and other shapes. Here, a cylinder is generated with a single point tool. As the tool reciprocates, the work is rotated at a definite rate of feed. When generating an elliptical cam shape, the work rotates and the centered distance between tool and work changes in timed relationship with the rotation of the work. We now apply the same generating principle to the cutting of a tri-lobe cam. Generating is here applied to the cutting of an external spur gear. A cutter in the form of a gear with relieved cutting edges is reciprocated as it rotates in harmony with the work. When cutting helical gears, a twisting motion is imparted to the cutter as it reciprocates. Internal gears, either helical or spur, are generated by locating the cutter at the right of the work center and rotating both cutter and work in the same direction. This principle can also be applied to cutting many other shapes. The hexagonal hole in this piece is being produced with a four-sided cutter. The curved surfaces on the cutter generate the straight sides of the hexagon, and the corners of the cutter generate a slight radius in the corners of the hexagon. The machine is geared in the ratio of 4 to 6. This is another example of generating a non-involute shape. The part is a two-lobe trip cam having a uniform rise of 1/1000th of an inch per degree on each lobe. Cutter and work are practically the same size, so the machine is geared 1 to 1. Here are some other parts generated on the gear shaper. These, together with the preceding examples, evidence the versatility of this machine and illustrate basic and special applications of the generating principle. Our main plant is in Springfield, Vermont. Whenever you have gear problems you would like to talk over with our engineers, come up to see us. Everybody at Fellows will do their best to make your visit a rewarding one.